And I think luckily, being at the back end of the day like this, everyone has really set the scene well for what I might say, and I'm never entirely sure what I'm going to say, so we'll see where we get to. But really, this is about, to touch on how do we find information in the data that we collect. And I want to probably emphasize some of the things that have come out from those talks earlier is, as an industry, we need to start to collect that data earlier in our projects and do it in a better way, because the information you can get out adds so much to the NPV of the project down the track. And that's a really important point that people are really starting to get into. And anyone that's seen the papers and work by Michael Samis and John Steed on mineral economics and the economics of this will see where people are starting to think about this. And I guess I should have had my own disclaimer before this, is that you'll typically see the same kind of slides in my talks, but they do evolve every time I talk. So yeah, bear with me. But really, this is the challenge that we face as an industry when we come to putting our first drill hole in and drilling our system out. So you can only go so far before you have to drill. The drill is the truth machine. It's the thing that tests our model, tests our hypothesis. We have to sample that rock. And the process of drilling is a cyclical process. We drill a hole to take a sample. We take a sample to measure stuff. We measure stuff because we want to make an interpretation. And we do all of that because we need to make a decision where to drill next, whether to call the hole, whether to walk away. And that process, that cycle, really for many years in our industry has taken too long. Making budget decisions on projects when you haven't got the data back from the lab is not a great position to be in. So one of the challenges we have around technology space is how do we address that challenge and make that cycle quicker and give the geoscientists and the people running those projects the information they need to make decisions they need in the time frame that makes an impact on that project. And you can see there are sort of highlighted aspects of that cycle. Certainly, the process of drilling is sampling the geology, but what we've really seen is an increase or an evolution in the technology we have available to us now to Geoscience. That is to measure something in the rocks. We can now do that in a much quicker way and much better quality data. Portable XRF, handheld libs, spectral systems, and the kind of way we interpret that mineralogy data. Turning data into information is a really important point. I'll touch on that because it's about supporting that decision by the team about what to do next in a timely manner. Ultimately, in our exploration projects, I've sort of written about this before, what we would really like to do is be able to fail fast. And I know that sounds horrendous, but that is actually, as an industry, what we need to do, because we need to take that investment and increase its chance of success by failing those projects that aren't going to make it fast. And that's a really uncomfortable place for a lot of people to be, but that is something we've got to do with this technology. The other thing, and I think this does also touch on points that have been made, Neris, I think you'll like this. I mean, I think one of the things we also need to do is we work in a project life cycle. That's what we do. We go and we drill our first drill hole, and we bring that project through a life cycle to, resource delineation, pre-feasibility. We mine it. There's a bunch of stuff that happens then. We process that, well, all of those processes, and actually we need another piece on the end here, which is around closure. We collect a load of data in that first drill hole that never gets used down this end of the project. But actually, some of that data we collect in exploration has enormous value at this point in the project. If you know here that you've got, what was it you said, Neris, acid, net acid consuming rocks. If you know that down there, you can make allowances for that and build that into your whole project plan. If you find it here, the cost of your project's enormous, okay? So while we're investing in that end, the net impact on NPV of our project can be so much greater by just allowing us to do things better at the very first point and allowing that data to be collected in a way that it's quality enough that it can flow through the whole project and be used by all of those silos, business units, people making decisions. And that's something that we are able to do now with the kind of technologies we have, and also touch on that as well. And I think this has become more and more simple as the day has gone on. So I'm going to really present it in a simple way. This is all we need to do, actually. So for our rocks, all we need to know is actually 4 things, right? So this shouldn't be hard. We need to know something about the mineralogy. We need to know something about the geochemistry. We do need to know something about petrophysical properties, and that can be texture, because, you know, is something foliated, it's going to break. Is something not foliated, it won't break. And we need to know something about spatial location, and the company I work for makes a significant amount of its revenue out of tools that get a spatial location. But you know, if we're putting all that money into drilling a drill hole to sample the geology, if we don't actually know accurately where that sample comes from, then we've just wasted all the data we've collected. So all of those 4 things are what we need, and we need to address how we're going to go and collect those. Because if you can improve or collect data against all of those 4 things, then you're basically increasing your rock knowledge, you're increasing your knowledge of the rock that you've drilled through and the decisions you can make. And this is a slide I stole from Fred Blaine, because I felt I needed to put a geometric thing in here, otherwise James was going to have a go at me. But you know, what's really important here for the geologists is the kind of things that we worry about in geological attributes interface really well with the metallurgy processing attributes as well. And you know, one of the things we need to do going forward is break those boundaries down. We have to be collecting data and looking at how those same data sets can be used to give us information in all the places we need to make decisions. And I guess that's where the science of AI, machine learning is one aspect of AI, you know, as computer vision is another aspect of AI. All of these things are coming to bear now. They're maturing to the point where we can actually take advantage of them and allow us to leverage or support us to make decisions and get value out of the data. Now, I will just say right up front that it's not all sweetness and lights. You know, this is a good example of what you get out of AI. If you don't understand what you're doing, you'll get back, the computer will give you back the right answer. Fisherman catches salmon in the river, right? That's what the AI art algorithm gave. Absolutely right. It's 100% right. You can't say that's wrong, but it's not what we wanted as a user of the algorithm. So one of the things we do need to do is we need to use the tools that are becoming available in AI, but we need to understand enough to know how we want to ask the questions and validate the answers coming back to us. Ultimately, I think our teams will be a blend of both data scientists working in close collaboration with geoscientists. I think that's the way that we're going to make a real win in our industry going forward. But yeah, I do like that. And anyone that's interested in learning more, actually, Cassie is a fantastic educator. She's the chief decision scientist for Google. Her AI introductory courses are all available online on YouTube. Just go in there. If someone chucks a buzz term at you, go and find out what it really means. So what can we do with good data? And you'll notice that word good, because this is really important as we go forward. If we want to do this properly, we have to collect good data. This is an example of an ecosystem. I won't touch too much on it, but one of the things we've heard about portable XRF a bit today. Again, I thought I'd better put this in, otherwise Todd would have a go at me, and I can't deal with 2 people having a go at me today. But here, this is an example of a kind of an ecosystem we've used in projects. This is something we do, Imdex hub system. We can connect evidence portable XRF to our hub to help geologists manage QA/QC, to manage the quality of that data. You can see the other really important thing I've done there is I've turned the sample into a pressed puck, which is the best quality sample you can present to a portable XRF, consistent, excellent detection limits, excellent data. This data then flows through to hub, gets QA/QC'd, and then the data flows onto IOGAS to do stuff, or it flows into your database to do stuff. At no point in this ecosystem here is anyone fiddling with the data. You're not exporting it as a CSV. You're not grappling with managing that data. It is managed for you. Why? Because we don't want our geologists to be burdened with that. We want them to be geologists doing this stuff. So if you get this piece right, then you start to get data like this. So here's a plot, a bivariate plot, silica on the x-axis, and a whole bunch of elements here. This is from a project that was done, a regional drilling project in South Australia. Diego, this is the MSDP data. These are 4 drill holes worth of data, all collected in that way with a portable XRF. So the first thing you can do is just look at the data like this. And what I've done is I've selected some elements here, and I've made a selection of elements that mean something to the rocks. So these are elements that would dictate lithology, really, more than anything else. Now, I've made that selection because I know the question I'm trying to ask, rock type. If it was about ore body type, if it was about alteration, I might make a different selection of elements. That's where the geologist needs to control the AI, not the other way around. So I've selected these. Now I can look at that and I can start to see structure in that data. It's actually beautiful data. There's real structure in that data. So immediately I can see, as a geoscientist, there's something in that data that I can start to pull apart. Now, the problem I have is that my brain doesn't work in 15 dimensions, and it kind of needs to be able to really pull that data apart. And that's where we're going to rely on the algorithms, the mathematics, to help support us to understand what's going on. So this is an example of a kind of a workflow here where I've taken that data. Don't forget how that data was collected. It's all digital. It's all QA/QC'd. It's all controlled. And this is just an example of a workflow that we can now do in the latest version of IAGAS, right? So James's 2023 latest favorite machine learning algorithm is UMAP. I love it. It's just, all it is an AI algorithm that is designed to reduce the dimensions. So I'm not working in 15 dimensions. I'm going to project all of that data into a 2-dimensional grid because I kind of can see what's going on. What's beautiful about UMAP actually is it preserves the relationships of the data. So if the data are very different, those relationships are preserved. If they're very similar, those relationships are preserved, even though you've projected it into 2 dimensions. So I've taken that data, I've done a UMAP, and then I've done k-means clustering. We've heard about that. So I'm just pulling out those different blobs, really. So I'm saying, you know, things that are red are all really similar. Things that are yellow are all really similar. And don't forget, I've chosen elements that are really related to lithology. And then what I've done is I've taken those color groups there because it's always good to color things. Once you color things, it becomes truth. And then I'm plotting these down hole. So here's my 4 drill holes, MSD 1 to 4. The color bar on the side there is the color groups here. And what we've got here is the 2 UMAP dimensions, 0 and 1 in this case, plotted as little bars down the side. So what I'm doing there is I'm presenting the data as information. I'm presenting it in a way where I've taken 15 lithological elements, reduced it down to something that I can present on these downhole plots that the geologist can then look at and go, I can see rock boundaries. I can see places where things are really similar. I can see places where they're different. What does that now mean to my logging? And we can, we can take this a bit further. So we can go back and look at that plot that we were looking at earlier. Now we've got the color groups on there. So we can start to see how that structure pans out. But then we can use something like another algorithm here. This is wavelet tessellation. So wavelet tessellation, what it's doing is it's taking that downhole plot and it's auto-picking the boundary. Now, what the beautiful thing about wavelet tessellation is it allows us to distinguish between the clumpers in the audience and the splitters. So on the right-hand side of this plot, on the right-hand side, you've got things clumped up. That's the biggest scale domains. And as you move left, things get finer and finer and finer, and they're the fine scale domains on the left. You can do this with any downhole signal. You can do it with any signal, actually. I've done it with Imdex's share price over time. And so what it allows you to do, you imagine presenting that now to the logging geologist. He's just laid the core out. You've got the technology working, so you're getting that data in near real time. You can run that workflow. In iOgas, actually now in version 8, you can build that workflow and deploy it out to your team. So they just click the button and run the new data through, and it presents a log to that geologist that is not telling him what everything is, but is guiding that logging geologist about where the critical differences are, where the boundaries are, where am I looking at similar rocks, different rocks, guiding them to add their information onto that framework. And by doing that, taking all of that burden away ahead of time. So this is just one aspect of using that data. And then, we can highlight some areas, and we can look at, I can highlight a cluster in the UMAP, and I can look at where that is in the rocks and that kind of stuff. So that technology exists today to allow us to do that. Now that's just asking one question: rock type, lithology. But it just shows you an example, and then you could start to go through. In some systems, you could look at ore body types, or you could look at the processing functions or something like that. But all of that is doable today if we have good data that's well QA, QC, that's consistently collected, that is consistent from collection to collection to collection campaign. If you do that, then you really do open up the value of being able to do a lot more of this. And and I guess that was kind of the chemistry side, and an example. And increasingly we're seeing these same ecosystems being brought to bear in the mineralogy side. So here's an example of I just put this porphyry diagram in because it just reminded me again that here, me as a geologist, I'm looking at an alteration model for a porphyry with all of that mineralogy. But I'm sure that someone like James and Dan and various other of you in the audience that think about geomet or processing look at some of those things and think, well, that rock won't break, that rock will cause problems in my processing plant. Here we have a model where we can spatially define how the things are going to process potentially. So let's go and use the data we're using as exploration geologists, mapping that out to then go and feed it back to our processing colleagues. I guess, one of the things that we're seeing a little bit of an evolution, and I'm not sure whether Dundee are doing this or not, but we have, again, interpreting spectral mineralogy is another little dark art that's been around for a while. You take a wiggly line and you turn it into mineralogy. There are now systems, AI Cirrus being one of them, which is using cloud-based AI technology to speed that process up and deliver quantified mineralogy. So this is something developed by OSPEC and is now part of the Imdex ecosystem. And again, we've got templates in iOgas where you can start to put that data on and look at what that mineralogy is. And that has impact both for the exploration geologists, but also then downstream in that project. And I just, again, stole this from Fred Blaine because Fred likes doing this kind of stuff. But, you can also, even if you haven't got the mineralogy data up front, even if you're just sitting there with some chemistry data from your first exploration campaign, there are methods and algorithms for turning that into mineralogy. And this is an example he'd done using linear programming, a simplex method for basically taking chemistry and figuring out what the optimum mineralogy would be, that would represent. And it's enough that you can start to get some patterns in iOgas. You can cluster that out. We can use the mineralogy, calculated mineralogy there to calculate a proxy density in this case, or an SG. We can bring that back into the downhole log. We can domain it out, although I'm not allowed to use the word domain because domain is 3D. I got told off by John Van, I think, once for doing that. But you can see how you can bring it into the log and bring it into the 3D space. And these workflows now are starting to exist to allow us to do this kind of work. So even if you've just got the chemistry, we can now start to do something with that data to give us information about something we hadn't thought about when we collected that data. So it's there, and it's there for us to use. There is value sitting in your databases. Let's hope that's not Excel or Access. There is value sitting in your databases that you can uncover and find this information. So once you got it into 3D space, of course, you can start to plot things like this. And we saw better examples from the Dundee example, but looking at chloride, looking at magnetite distribution. So that's just calculated on the exploration chemistry. So, really, I think one of the things I touched on there is early data collection is critical, and do it well, because the value will exist in that data for your whole project lifecycle. And the information should support decisions, and it will improve your overall project MPV. And data consistency and quality are critical to get this right. If you have quick data that hasn't been QA/QC'd, you'll struggle when you come to try and release that value further down the track. There's other stuff in my head, but I could talk about that over a bit. All right, so thanks very much, guys.
Before taking talk away, we have time for a question or two. Anything for James? Very interesting at the end there, that partitioning of geochemistry into the mineralogy. Is that done with ICD or
Yeah, so the more complete the assay, the easier it is. But there are certain things you can do with partial assays as well. Yeah, there's Red's very good at it. There's about 4 or 5 different schemes for doing this, but as a way of getting something out of the data you've collected to give you an idea of what's going on, it's a completely valid process.
Is that something that might be integrated into gas, or is already squirreled away in it?
Pretty sure there's a bunch of tickets in the backlog, and the more people that ask for it, yep, it's on the roadmap for sure. Yeah.
A question about data, and did it ever help skipping assays?
Does it what, sorry?
Did it ever help you with skipping doing assays and waiting for lab results?
I mean, I suppose my history has been, I've never been the person to do this in anger in an exploration project, so I can't give you the experience of that. But certainly the quality of that portable, I've got to be careful who's in the room. The quality of that portable XRF data done correctly, the reality these days is that the device itself is going to give you really high quality data. And all of the challenges now exist in the sample that you present to it and the consistency at which you do the process. But if you get that right, there's a lot you can do that means you can reduce some of that other work. Cool. Thanks.